Okay, so we're gonna work on this problem, and we see we have this uniform rod of weight 8 pounds and radius 10 inches, and it's attached to a pin at C and to cable AB, and we have to determine the tension in the cable and the reactance at C. So one thing to think about in this problem is that B does not. Let me hide that. Oops. So B here does not exert any kind of a reaction because it's just holding the tension, the piece of wire or whatever in place. So we don't have any reactance at B. We do have reactance at C, and what I want to start with is the sum of the torques. And so the way I like to think about this one is, or the sum of the moments. So I want to do the sum of the moments, and I know it's equal to 0 because this rod is not rotating. So what I want to think about first is imagine if the rod was just like this, right, attached to C. Um, and it looks like it could rotate here, right? So one of the things we know, so we took the tension wire away, and one of the things we know is we know that our location of the center of mass of the rod is somewhere like around here, right? And we know from our equations when we were doing centroids that for a quarter of a circle that the x distance, so the distance, like we'll do that, and we'll say this distance is x bar, and this distance here is y bar. Right, so x bar is this distance, and so we know that both x bar is equal to y bar is equal to 2r over pi. And we know that r is equal to 10 inches, so we're going to have 20 over pi. So each of those values. So that's where our center of mass is going to be. What I want to think about, we're going back to moment. So this thing is going to rotate. And so without the tension here, I know this rod is just going to fall, right? So I'm going to have something like, I'm not a very good drawer, but something like this, right? If it were to fall, something like, or not even that. And I forgot how to draw here, and I think I can erase or undo somewhere. Let's see. Draw, insert. Oh, there was the eraser. I just saw it. I can erase that. So something like, uh, back to my pen. So like something like, I guess that. So it would fall, right? So it's gonna rotate. Then it's gonna go rotate down like that. And so what we need to do is think about that component. That rotate down is one of the components of the moment, right? Its ability to rotate, and it's going to rotate. Imagine that this direction is the x direction, and this direction is the y direction, or yeah. So this is y, and this is the x direction. Then out of the page, or into the page is the z direction. So into or out of the page is z direction. So my moment is going to be around z because it's going to rotate down and it's going to be rotating. Like imagine if I said like this, the dot was like into the page. This thing is going to rotate around it like that, around the z, around c. Uh, it's going to rotate around z at c, and so we're going to call the moment at z. And so the first component we're going to take is the weight, the of the little bar is going to be, we'll call it just fg times r. And so the r that I'm going to take is the 2r over pi. And so why am I doing that? That's a good question. And it's because so 2r over pi. And then, okay, so I've got that. So I'm assuming that that's my distance here. And I'm not really sure why I didn't take, oh, right. Okay, so why did I take this distance? Well, if I think about it, I could imagine I want to take, so this is really my R, right? But I need to take the component of R that's like how far it is perpendicular to the axis, right? So this is my, like, the R component that I want, right? So what I'm doing is I'm bringing this, so what I have is I've got, so let's just say this is into or out of the page. My R is out like this, and my FG is down, right? Like this. But when I take the moment, I need the distance away from the z-axis. Remember, the z-axis is into or out of the page, so I need this distance here, right? And this distance here, if I look back, so I'm this distance here is the same as this distance here, and that's this x value that we have. So that's why we have 2r over pi. So I have one of the components. So now let's see, the other component that I need is putting that tension piece back, right? So the tension piece, if the bar falls without the tension piece, then the tension is pulling on the bar, right? So the tension is pulling on the bar this way, right? So that's pulling around the axis. So what I can do is I can say, okay, if I'm pulling around the axis, so here's my axis, and I have this force that's up here, right? That's pulling, that's making it go this way. So that's like in the other direction. So I know I'm going to have a minus. And so this is the tension force pulling that rod that way. And I can slide this over. So my R looks like this, but I need the component that's perpendicular. So I need this component right here. So this is the part right there that I'm looking for. And so that part right there is the radius. It's the distance from here, right? That's the radius that I need. And so that's how I'm thinking about it, is I need this, right? This piece right here is my tension, but I need the part that is perpendicular to my axis. So I need this part right here. So that means I'm going to have the tension times the radius is equal to 0. So I can plug in for this. I can say, I'll bring it down here. So my FG, so I'm going to have FG times 2r over pi minus TR equals 0. And now I can cancel my r's because they're in both components. And I can solve for t. So I'm going to add t to this side, add t to this side. I can cancel them on that side. So I'm going to have FG times 2 over pi is equal to t. So I can plug in. So t is equal to 2 times 8, because we're told the weight, over pi. And that's how we get 2 is equal to 5.09 pounds. Okay, that's part A. So we'll call this part A. Now B, we need to find the reaction forces, right? So B, I need to find Cx and Cy. Okay, so if I just go back down here, and let's see if I can copy that. Maybe home. I can copy. Let's see if I can go down here and paste this in. Home and paste here. I guess not. Anyway. All right, so I've got this piece, and I want the reaction forces. So my reaction forces, when this tension is pulling this way on the rod, that's my tension. So I know that the C X has to be this way. And then I know that remember, gravity around here is pulling that way. So my CY has to be this way. Oops. This is my CY. So I know the directions based on what the other forces give me, right? So I know that this thing isn't moving, so that's why the T and the CX have to balance. And I know it's not moving, so the force down of gravity has to be balanced by CY. So that means I just really have two equations. Some of the forces in X equals 0, and some of the forces in Y equals 0. And so I have my tension is pointing, remember my tension's pointing this way, and Cx is pointing this way. So this is Cx, and this is my tension. So I'm going to say tension minus Cx equals 0. So Cx is going to equal tension, and therefore Cx is equal to 5.09 pounds. And for Fy, remember my Fg is down, and my Cy is up. So I'm going to have Cy minus Fg is equal to 0. So Cy is equal to Fg, which is the same as weight. So Cy is equal to 8 pounds.